Hi, today we're going to learn about solving linear systems using matrices, and I would consider this under linear algebra, but it also can happen in pre-cal, so you'll see it in both. So first off, I'm going to in this section I introduced matrices, augmented matrices. I went over pivot and pivot column and row of operation. I will go over Gaussian elimination and how to solve a system equation using Gaussian elimination. So over here we have before we start, let's start with what is a matrix. Is basically, it goes by the rows by columns. So an example would be 3 by 2, 3 by 3, right? So, and then an augmented matrix is, here's something, okay, so they give you a system of equations, x minus 3 equals 11 and 2x plus y equals 1. So what kind of matrix is this? This is a 2 by 3 because it has 2 rows, 1, 2, and it has 3 columns, 1, 2, 3. So if we were to put it in a matrix, we just use the coefficient. So over the x, so we said this is about a 2 by 3, so we're going to make a 2 by 3 matrix, and then we just put the coefficient. So over here we has a 1, right? Because if it's by itself, it has an invisible 1. So this is 1, 2, -3, 1, and then this vertical line represents an equal sign because we have an equal, and then we put the our constant 11 and 1, the last part. So that's how you do this. So this is an augmented matrix. Okay, so then we also have what's called a row of operations. So these are the only things you can do for a row of operations. You can interchange interchange two rows of matrix, multiply every entry in a row by the same non-zero real number, or you multiply it by scalar. You can either add to a row to a non-zero multiple of another row, so you can add or subtract rows. This might sound weird, but when we do the problems, it's going to make all sense. And then we have what's also called Gaussian elimination. So let's say you have a matrix of x minus 3, y equals 11. A system of equation, x minus 3 equals 11 and 2x plus y equals 11. First step I would do is put it in matrix form. So this is what kind of matrix is this? This has 2 rows, so it's 2 by, and then goes by column. So 1, 2, 3. So it's a 2 by 3. So now we just put the coefficient 1, 2, -3, 1, and then the solid line for equal sign, and then 11, 1 is our coefficient. So our goal is to use the row of operation to make it look like a pivot of 1, 0, 0, 1, and then a number, because we don't know what that is, because we're going to use the row of we want to use the row of operation to make it look like this. So this is a 2 by 3. And then a 3 by 4 would look something like this. Notice how we have a 1 here, 1 here, and 1 here. And then we have a 0 here, a 0 here, a 0 here. And then we don't have a 0 here. It's going to be a number, but we don't know that number because a number here, number here, number here. This is also called the row echelon form, right? Now, people say, what's the difference between row echelon form and reduced row echelon form? So again, this is a 3 by 4, so reduced is, notice how this is a 0, this is all ones, right? The same, it looks exactly like this, 0, 0 here in the bottom, and then the only difference is instead of a number, it's going to be, we have to make it 0, 0, and 0 over here. So there, for row echelon, reduced row echelon form, there is no substitution. So we remember this is going to be our x, y, and z. So z is going to be a number, and then x is going to be a number, y is going to be a number, and x is going to be a number. There's no substitution. For row echelon form, there is a substitution. So this is going to be x, y, z. Z is going to be a number, And then what you do is you're going to have to substitute for y. It's going to be y plus a number equals a number. So you got to substitute, and then you got to do a little bit more work, but either way, you're going to get the same answer. So that's the difference between row echelon form and reduced row echelon form. There's no substitution here. For row echelon form, there is substitution. Okay, so the Gaussian elimination method for an independent system of two equation, just like I went over from this part, we just want to make it look for 2 by 3. We want this to be all ones and we want this to be all zeros. We have to use the row of operations to make it look like this. So over here, notice how we have a 1 here. It's called a pivot. We want all that to be ones. And then over here we have a pivot column because it has a 0. So 1 and 0, this is a pivot column. So 3 by 4, you could just make it make this pivots all ones and this all zeros. We could leave this, we don't have to make this zeros. We could just make it a number and then just do substitution. So let's do some problems. So it says, first one says, determine the size of a matrix. So you have -5, 99, 0, 12, 6, and 0. So remember what a matrix is? A matrix goes by row by column. So let's count how many rows this has. So this is going to be 1, 2, 3. There's 3 rows by columns, and we have how many columns? 1, 2. So this is just a 3 by 2 matrix. That was simple, right? Okay, now it says write the augmented form. Write the augmented matrix for each system equation. So let's look at this. We have x plus 3y minus z equals 5, and then we have x plus z equals 0. We do not have a y, so we're going to make sure we're going to put a 0 wherever there's a y. And then this 5 is 0 is what called our constant. And then first off, let's figure out what is the size of this matrix. So how many rows? 1, 2. 2. And then how many columns? 1, 2, 3. Remember there's a y, so it's going to be 3. And then the column, the constant is 1, 2, 3. It would be 2 by 4. Now I'm going to put in the matrix, so we just put the coefficient. So this is going to be 1 here, and then 1 here because x is all ones. What about our y's? It's going to be a 3 here. On the second system equation, we don't have a y, so we have to put a 0. And then for the z, it's going to be the coefficient, so it's going to be -1, and then +1, right? Because there's a +1 here. And then we put the solid line because that means equal. And then we put our constant, so it's going to be 5 and 0. So that is our augmented matrix. Simple so far, right? And then the question says write the system equation represented by of each augmented matrix. So we got to write the system equation, so it's kind of like going backwards, right? Remember they give us a system equation the first time, and then we have to put in a matrix. Now we have to go back, so we have to put this matrix into a system of equations. So first off is I'm going to figure out what size is this matrix. So how many rows does it have? 1, 2, 3. And then by columns, so how many columns do we have? 1, 2, 3, 4. So this is going to be a 3 by 4 matrix. And see that here we could call this x, this column x, y, z, or you could say a, b, c. It doesn't really matter. I'm just gonna stick with x, y, and z because that's just very common. Then what we have to do is, okay, so we know this solid line means equal, right? And then this column is our constant. So we know our coefficient, so it's going to be 1x, or x, minus y, because that is our coefficient, and the z is plus 2z equals 1. So I'm going across, and then this is going to be 0. So there's no x, so we can skip that. We have a y, it's going to be positive y. And then we have a z, which is plus 4z equals 3. And over in the last row, we have no x, we have no y, we have no z, and we have no constant. So we'll just leave it blank because there's nothing. So this is our system of equation from our augmented matrix. Not too hard for right now, right? Okay. Now I think we're going to do some row of operations. So it says perform the indicated row of operation on the given augmented matrix. So we have to, okay, so we're multiplying the scalar 3 to row 1 plus adding row 2, and this is going to be our new row 2. So our new row 2, we don't care about row 1 because we're not touching that, because well, yeah, we're not touching our we're not touching it row 1, but we're only touching row 2. So what we can do is write whatever row 1 is. So it's going to be 1, -2, and then this solid line. So it says we're going to multiply 3 by row 1 plus row 2. So here's row 1. So it's going to be 3 times row 1, so that's a 1, plus row 2. Here's row 2. That's going to be a -3. So negative 3 times 1 is 3, plus -3 is 0, right? So this is going to be our first row. And then our second column over here is going to be, so it's going to be 3 times -2 plus row 2, which is, here's a 5. So this is -6 plus 5. What is that going to be? -1. And then the last one, the last column, so it's going to be 3 times row 1. Here's row 1, so it's going to be 3 times 1 plus row 2, and then 0 is on the row 2. So 3 plus 0 is 3. So that is our new, this is our new row 2. So that's how you do row of operation. We multiplied a scalar plus a row 2, and that gave us a row 2. Because we need to do this when we use Gaussian elimination. Okay, so it says solve each system using Gaussian elimination. State whether the system is independent, dependent, or inconsistent. So it says, first off, I will make this. I'm gonna get all the x. This looks this isn't we have all. Okay, I want all the variables on one side and all the constants on one side. So over here, y plus 4 minus 2x, I'm going to add 2x. Because I don't want all the constants on one side and all the variables on this side. So, and over here, the second system equation, I'm going to get rid of this y. I'm going to subtract y from both sides. So you're going to be so our new system equation is going to be 2x plus y equals 4. And then this is going to be x minus y equals 8. Now we could put it in a matrix. So this would be this would be a 1, 2. This is going to be a 2 by 3 matrix. So in matrix form, we just put the coefficients. So here's a 2, here's a 1, and then the solid line means equal. So this is going to be 4, and then this is going to be a 1 minus 1, right? Because these are all coefficients 1. So we have our augmented matrix. Remember, Gaussian elimination, we have to make it look like this. Right? That is our goal. And how we do that is we're going to use row of operation. So over here, let's look at the diagonal, 2 and negative 1. I don't care about making it 1 right now because I could just multiply scalar by that row to give it a 1. What I do care is about making this diagonal 1 and 1 to make it 0. So let me just tell you the steps. So what I'm going to do is get all the constants and variables on one side. That was step 1. Get all constant on one side. And then what I'm going to do is I put it in matrix form. I did that, right? Check. Into matrix form. And then now I'm going to use row of operation. I'm going to use row of operation to put it into row echelon form. To put into row echelon form. Also known as Gaussian elimination. Okay, so I want this diagonal to be, this 1 and 1 to make it 0. So let's change the first row. Wait, no, I'll change the second row. There's so many ways you can do it. You could change the first row first, or so what I'm going to do is I'm going to row 1 minus 2 times row 2. So I'm going to multiply the scalar of 2 to row 2, and this should give us a new row. So I didn't touch the first row, right? I'm not going to touch it. I have to do this little by little, so I'm not touching the first row. So I could just bring that down because it hasn't been touched. I will manipulate the second row. So it says row 1 minus 2 row 2. So here's row 1. So it's here. We're going to use 2 minus 2 row 2. So it's like saying 2 times row 2 has a 1, so it's going to be 2 times 1. So 2 minus 2 is 0. And then let's do the second column. So row 1 is 1 minus 2 times row 2, which is negative 1. So that becomes positive, right? 2 negatives become positive. So 2 plus 1 is 3. And then this column right here, we said, so row 1 is 4. And then minus 2 row 2, so it's going to be 2 negatives, because did I do this right? Okay, so we said row 1, here's 4 minus a negative, so times it by 8, so great. Okay, so row 1 is 4 minus 2 row 2 this is going to give you negative 12. Good. Okay, so we have a 0 here. We want this to be 0 as well, so now we can manipulate the first row. I will say I'll multiply negative 3 to row 1 plus row 2. And this will give us a new row 1. Row 2 hasn't changed, so we can just leave it as it is. So we have 0, 3, negative 12. Okay, so I'm multiplying negative 3, a scalar, negative 3 to row 1, plus row 2. So 2 times negative 3 is negative 6, plus row 2, which is 0, because 0 is on row 2. So this is going to be negative 6. Okay, now negative 3 times row 1, so that row 1 has a 1, plus row 2, which is 3. Right? This is row 2. So that's negative 3 plus 3 is 0. Good, that's what we want. We want this to be diagonal to be 0. And then, we say row negative, so negative 3 times 4, because negative 3 times row 1, so here's 4, plus row 2, which is negative 12. So negative 12 plus negative 12 is negative 24. Good. Now, we did the hard part. That's the hard part. Now we have to do the easy part, because we got this diagonal 0. That was the hardest. Now we have to make this diagonal to positive 1. So what you can do is just simply multiply each row by a scalar. So for row 1, I can do this all at once. I can multiply this by negative 1, 6. And that gives us a new row 1. And for row 2, we can multiply this by a positive scalar of 1/3. So this is going to be positive 1, because negative 6 times negative 1/6 is positive 1, right? And then negative 1/6 times 0 is still 0. And then negative 1/6 times negative 24 is positive 4. And then for row 2, we're using this row, right, this matrix. Row 2 is 1/3 times 0 is 0. 1/3 times row 2, so we have a 3 here, right? That's going to be 1. And then 1/3 times negative 12, which is negative 4. Good. So we have it in this form, right? We have a diagonal of 1 here, 1, 1, or a pivot at 1, 1, and then we have diagonals of 0. So we could call this column X, and we could call this column Y. So over here, so here's 1, so it's going to be 1 times Y is Y, so that equals negative 4. And then our X is 1, So 1 times x is x, and then that's going to equal to our constant, which is 4. So we have 4 comma negative 4. That is our solution. Now they say, is it independent, dependent, or inconsistent? So what do we know? We know that if something is independent, we have one solution. So we have one solution. So we got the last step is to check it if it fits into the equation, to the solution. So I'll use the first equation, this one. So we said our y is negative 4. So does negative 4 equal 4 minus 2? And our x is positive 4. So 4 minus negative 4 is negative 8. So 4 minus negative 8, so that's negative 4. So that's true. So we know it's consistent, independent, and it's independent, so we have one solution. So this was solving Gaussian elimination by using 2 by 3. So this was solving a Gaussian elimination by 2 or by 3. So it wasn't, first we had to do is get constants on one side and variables on one side, and then we put it in matrix form, and then we had to use row of operation to make it look like this. Now the other one is I think it's going to be a 3 by 4. Yeah. So let me just write the steps here. Step 1, we're going to have to put it into matrix. Step 2 is we're going to use row of operation. And then step 3 is substitution. So what did we say? The first step is to put in matrix. So this is going to be 1, 2, 3. So this is going to be a 3 by column. So 1, 2, 3, 3 by 4. So we're just going to put the coefficient. I'm going to go downwards column. So here's 2, 1, 1, because A has a 1 here and positive 1 here, invisible 1. This is going to be a negative 2 because the coefficient of B is negative 2, 1, and then negative 3. And then the C is going to be 1 here, negative 3 here, positive 1, and the solid line because it means equal. And then we're going to put our constants. So it's going to be negative 2, 3, and negative 5. So do you remember Gaussian elimination? We want to make it look like 1, 0, 0, number, 1, number, 0, 1. It's going to be a number, and a number. So we want this to be all diagonals, and we want everything below here, we want it to be 0. And we don't care about making this zeros because this is Gaussian elimination. You can make this all 0, right, if you don't want to do substitution. So first step, so we're going to do row of operations. So I already done this, so I already done this, so I'm just going to show you what I did for each row. If you're barely doing this, I would just do the math little by little, but I've already done it, so I could just put the answers. So first step, I'm going to manipulate the row 2. So I'm going to do row 1 minus 2 row 2. So our new row 2 is going to be 0, negative 4, 7, and then negative 8. And row 1 and row 3 has not been touched, so it's going to be 2, negative 2, 1, negative 2, 1, negative 3, 1, and negative 5. There's so many ways you could have done it. My way isn't. There's just so many ways, but we'll eventually get the same answer. Then I'm going to manipulate the row 3. So what I'm going to do is I'm going to do row 1 minus negative 2 row 3. So I'm going to row 1 minus the scalar negative 2 row 3, and then that should give us our new row 3. So this is going to be 0, 4, negative 1, and then 8. And then row 2 and row 1 hasn't been touched, so we'll just leave it the same. So this is going to be 0, negative 4, 7, negative 8, 2, negative 2, 1, and negative 2. I'm going to manipulate row 3 again, so I'm going to put it right here. I'm going to do row 2 plus row 3. That will give us our new row 3. So this will give us 0, 0, 6, 0. Row 2 and row 1 hasn't been touched, so we're just going to leave it as it is. So this hasn't been touched. So 0, negative 4, 7. Notice that I'm only doing one row of operation at one time, because you can make mistakes if you do two row of operate, like 2 rows, if you manipulate 2 rows at a time. The only time I would do when you could do more than one row of operation is when you're multiplying the scalar to get it all one. So my last step is I'm going to multiply each row by a scalar. So I'm going to do 1/2 times row 1 times row 1. That'll give us our new row 1. And then for row 2, we're going to do multiplied by negative 1/4 to row 2, and that'll give us our new row 2. And then for the third row, I'm going to multiply the scalar of 1/6, and that'll give us our new row 3. That is the only time I will use more than one rows of operation, when I'm going to multiply by a scalar to give it all diagonals of 1. So this is going to give us our new matrix 1, negative 1 times about 1/2. This will give us negative 1, 0, 1, and it's okay to get fractions. It's going to be 0, 0, 1, and 0. So remember this column, we said this is going to be A column, this is going to be B column, this is going to be C. So over here, let's do the last column, the last row. So we said our coefficient is 1, so it's going to be 1 times C, or C, and it's going to equal to our constant, so it's going to be 0. Now I have to do substitution, because we didn't make this all 0, 0, because we don't have to, because it's Gaussian elimination. So this is going to be B, right? 1 times B, or B, minus 7/4, because that's our coefficient, 7/4. C equals the constant equals 2. So we know C is 0, so that's easy. C 7/4 times 0 is going to be 0, so it's going to be B equals 2. So we know what B is. Now we know, let's find A. So it's going to be A. I'm looking at this row. 1 times A is A, and then minus B, because that negative 1 is our coefficient, negative B, and then plus 1/2, that's going to be our C, equals negative 1. So we know A is, we don't know what A is, we know what B is, minus 2, And then we know c is 0, so that's going to be 0. 1/2 times 0 is 0. Equals -1, and then to solve for a, you just add 2. So a equals 1. And then what you do is you could put it back into the original first equation, and then that should give us -2. And I already checked, so I don't have to do it again, but if you don't believe me, you could just check it. So our solution, I'll put it right here, is 1, 2, and 0, right? Our a is 1, our b is 2, and our c is 0. And remember, if you have one solution, and if you put it back to the original equation, one of them, and if it's true, or I mean all of them, and if it's all true, that means you have one solution, and we all know that one solution makes it independent. So there you go. This is our solving linear system of using matrices, and this is under linear algebra, and it can be pre-calc. Sometimes it can be, because I've tutored pre-calc and this does pop up. So if you like my video, please like it and subscribe. Okay, thanks.